Welcome everyone. Welcome to this ACES webinar series, our technology showcase series. ACES is an ARC-funded Centre of Excellence headquartered here in Wollongong in Australia, in partnership with a number of other Australian universities and international universities. Here at ACES, we are charged with the design and discovery of new electromaterials and the integration of those into structures which enable us to have practical applications in the areas of energy and in health. This series of the Technology Showcase series is really special for us over the next few weeks, and this is the first of them today. We've identified a number of technologies that's built on many years of fundamental research, but we believe is now in a position to undergo exciting translational opportunities into practical application. So based on great breakthroughs in fundamental science and engineering and positioned for translation, we're going to expose to you a number of technologies in the coming weeks. Today's is a very exciting technology, the soft robotic prosthetic hand, which Gursel and his team will introduce to you. And in each of these areas, including today, we're keen to establish new partnerships that can help us accelerate progress. That's the real focus of this series in coming weeks, is to introduce to you fundamental breakthroughs that are ready for translation and where that translation can be accelerated by forming new partnerships. So this area has been developed by a highly talented team of our colleagues in ACES, led by Professor Gursel Alici, and I'm going to hand over to Gursel. Thank you.
Thank you very much, Gordon, and welcome to the showcase, everybody. And I thank all our attendees today, collaborators, and Professor Gordon Wallace, who is the director of ACES, for giving us this opportunity to present our project on prosthetic hand, soft robotics for prosthetic devices, specifically on a specific project we have worked in the last 5+ years on a transradial prosthetic hand. Without saying more than this one, I would like to share a PowerPoint slideshow and show you what we aim, what we have done so far, and then after that one, we are going to demonstrate the hand live through this screen. As you can see, there are some hands on the table, and hopefully they will give us a hand to share you what we have done and what we have achieved and what we can do, and whether there can be some collaboration opportunities for anybody out there. So without saying more than this one, I would like to now share the slides I have to tell you more about the technology, its details, and what we have been doing, etc. Yes, as Gordon mentioned, ACES will present a number of showcases. This is the first one on the ACES ZOW prosthetic hand. My name is Gursel Alici, as Gordon mentioned. I'm the leader of the research program on soft robotics for prosthetic devices. And with me, I have my colleague, project researcher, Dr. Zhou. So he's going to demonstrate the hand. And he tested, he worked hard, he made sure that all the batteries, including our batteries, are fully charged. So, which is great. So, as I mentioned, we do research on soft robotics. So the main aim is to use soft, smart, and printable materials to establish novel actuation and sensing concepts and their applications in new applications, their applications in robotic applications. And they can be applied in a range of applications, such as artificial muscles, sensorized grippers, human-machine interface, soft sensors for any devices to communicate with the outside world, sensors for prosthetic hands, etc. So there are plenty of applications, and today we have specifically talked about one specific application, which is a prosthetic hand for users who don't have a hand below the elbow. transradial prosthetic hands. As you may know, there are 7 states of hand or arm amputation. Rather than focusing on all of them, we specifically selected transradial hands. So when we do this one, we also put some questions in front of us. First question was, can we restore normality for people with hand difference through technology? And ACES is one of the unique places where we combine cutting-edge technology of additive manufacturing, smart materials, and soft robotics to bring a new technology, some new technologies, to bring prosthetic devices, specifically hands, transradial hands, one step closer to their natural counterparts. And we know that replacing a natural counterpart is very challenging. So we put an aim in front of us to come one step closer. I think we did, and we are also aiming more steps. Maybe I should say more about this one. What is the main problem in prosthetic devices? If you look at the current prosthetic devices on the market, they are highly sophisticated. Based on progress in mechatronic systems, actuators, and sensors, their mechanical design, their operation are brilliant, no issues. The main problem is their control, their bilateral control and communication with the user. So user should feel that the hand, in our case, is part of their body. So the current hands have low embodiment, and this causes significant problems such as low acceptance. I will tell you later in a minute, we ran a survey in 2017 in Australia to ask them what do they want in a prosthetic hand. So one of the issues they raised and also raised in the literature is that although they have a prosthetic hand, they don't want to use it at least 1/3 of the times because of many reasons. I will tell you the many reasons. But one of the main reasons is functionality, low embodiment, it being heavy, and its functions are very limited. And it's coming back to the basic question of bilateral control. Can you sense the intention of the user non-invasively, convert into control commands, drive the robot, drive the hand, including the wrists and the fingers? That's fine, but equally importantly, can you send that signal, contact, the touch sensing back to the user who can feel their hand is touching something, doing something, rather than relying on their visual feedback, and which puts significant cognitive burden on the users. And that eventually leads to low acceptance and not benefiting from this technology. So what we did here, different than many groups, is that we followed user-centered design methodology. And that comes to the survey I mentioned. Also, we aim to embed ethical consideration in the hand project. And to this aim, we organized a survey together with our colleagues in another team, ethics, policy, and public engagement team. We designed a survey and we sent to various places in Australia to get answers for this fundamental question. And here are some of the answers I would like to share with you, and then end up with the features we put in our head. So when we analyzed those survey results, they gave these 3 reasons why they don't want to wear prosthetic hands: size and weight. They are too heavy. Although the weight is not as heavy as our natural hand because it's not part of their body, they feel like it's a foreign object. Size is okay, you can size it, but still I think being heavy is a problem. Functionality and dexterity, these are very important reasons. I don't want to spend too much time. We got 2 papers on that one. If anybody wants, they can do it, they can look at it. Another one, they want to change their prosthetic hands with very similar reasons. You see, now we got reliability. Financial capacity, of course, is always a problem. We found that 77% of the people who participate in our survey relied on the government schemes. So it's essential to make them affordable. As you may know, they're very expensive, the current ones. And some information we collected was problems, very similar. You see, it leads to the same points, limited functionality. The current hands can do open and close. And if you want to add a feature called such as pattern recognition to identify the gesture in a non-invasive way, they have to pay very high amount of money, which is not affordable. Again, size and weight and reliability. Another issue they raised was sensory feedback. As I mentioned, this is a traditional multi-million-dollar problem. I'm going to show you some videos, some results as well, how we have made some progress in sensory feedback. The main reason they want to use sensory feedback, they want to control their grip strength. The current hands open and close the finger, it doesn't stop where it should, unless you see visually as the user in the loop, you just control the signal, the amount of expansion and contraction you put on your muscles and the signal to open the grip strength. So these are some problems. So based on this one, we came with a list of characteristics. So in a way, as we said, it's user-based. From the users, we collected the information and we came with this set of characteristics. You see, low weight, low power, low cost. This is technical low footprint, means we don't want it to be too complex. We didn't want to have too many motors, actuators, and it's called under-actuation. And when we talk to these people, they don't want too many grasping or gestures. They want 6, 7 standard grasping tasks. And they want programmable compliance, which comes to controlling the gripping force. But those red points are the bottlenecks. These are the ones like natural control, as I mentioned. Can we have surface mountable, non-invasive electrodes? Yes, they have surface electromyography electrodes, but they have lots of problems. And in the last 5 years, we developed a set of electrodes which outperforms surface electromyography electrodes. And the electrodes that we developed can be worn on the shirts, on the clothes. It doesn't have to be in contact with the skin directly like the current surface electromyography electrodes. The next one is feedback. I mentioned, I will tell you more later. Of course, the other ones did. So these are the ones we came, and based on this one, we made significant progress. You can see some images. If you are interested in, you can contact me. I can send you the copies of our papers, or you can search our names and our address, and you can get some of our papers on ACES prosthetic hands. And here, deliberately, I put this word. I said not necessarily with surface electromyography electrodes. So what we did, I just highlighted some keywords. We made sure that it's monolithic, it's one piece. As you can see on the screen, I will maybe zoom later to show some of our hands. We made sure that it's one piece. And that helped to make it low footprint. We embedded soft sensors. Maybe I'll show later. We got some fingers. Maybe when before house starts, I will show a finger where we put the sensors as part of the finger, like our natural fingers. So we try to make sure that we embed our important elements as part of the mechanical design. It's customizable because of 3D printing. We can customize. We were told that prosthetic hand users want hands for different purposes, for work, for social events, for casual events. They want hands which can be customized to their purpose. Intrinsically complying, you need to make sure that when it wraps, touch the objects, it doesn't damage it. And we achieve this one too. And we can have diverse grasps. Low weight and costs is certainly the weight of the current hands we are going to show you is 240 grams. It's half of the typical prosthetic hands on the market and half of the weight of the natural hands. Intuitive pattern recognition. We are currently working on this one, trying to use 2 electrodes on the current hand, whether we can come with an affordable retrofitting system to identify the user's intention and control the hands. Actually, we did this and we tested with some prosthetic hand users in Prince of Wales Hospital in Renwick in the Department of Rehabilitation Medicine. And we found that we can recognize up to 5 patterns, although 4 patterns can be recognized very accurately 90+% of the times. And that's also a significant progress. And the sensory feedback. I need to tell you more about sensory feedback, then I will finish. For the sensory feedback, it's a very important feature. We didn't want to target invasive techniques. When we talked to prosthetic hand users, one thing they told us was that they were sick of another surgery. They are sick of having an invasive system which has to be implanted in their body. Therefore, we targeted 2 non-invasive sensory feedback techniques. One of them is called mechanotactile feedback. And this technique is based on a small electric motor driven by a mechanical crank, driving a mechanical crank, this blue one, and is connected to a small electric motor here in the background. And this crank, this arm rotates in proportion to the contact force applied to the thumb, to the pointer, and remaining 3 fingers. Of course, you can put many sensors on many fingers. So we try to use 3 electric motors put on an armband like this. So this is one motor responsible for the thumb, for example, is responsible for the pointer, is responsible for the 3 remaining fingers. So we tested this one with 6 real users in Prince of Wales Hospital. I will show you a brief video. And the second non-invasive technique we tested was that based on giving some constant current, using a constant neurostimulator, applying a constant current in proportion to the contact force. So what we did here, friends, we just made our own electrodes. This circular one, maybe I'll show you this one. I got samples in my hand. I don't think you will see it now here, but when I come closer to the hands, when we demonstrate, I will show you this electrode consisting of anode and cathode covered with graphene. So this is all 3D printed. So what we try to do, we try to use progress in cutting edge technologies to solve some of the ongoing challenging problems in prosthetic hands. And what we found when we used this electrotactile one, we found that the users can localize the sensation. They can tell that sensation is applied. We try to apply on their upper arm because lower arm is being used for the EMG electrodes to control their prosthetic hands. So this is also something we came, it's higher comfort. We also asked them after the test, they gave us their feedback, and also lower interference with EMG, electromyography electrodes, which are used to control the hand. Without saying more than this one, let me show you this video. This video is recorded in the hospital environment. Here we got a prosthetic hand user. She had a hook type hand. Rather than modifying their hand, what we did, we built a sensorized object, this blue box. And this circular blue area is a sensor, and there's another one on the other side. And we told the users to grip this object. And we also put a box here to put these weights inside the box to take this box from one side of this this red or orange obstacle to the other side with minimum, almost no training. So the idea was as if this object is an egg. If you apply too much force, you are going to damage. If you apply too little force, it's going to slip and drop. So the idea was to control the pinching force or the gripping force to make sure that the user applies minimum force. When they apply more force initially, I'm going to show you a graph, and this armband, which carries either a small electric motor or these electrodes, you may not see it, which applies a constant current on the upper arm in proportion to the contact force, and they know when the current is too high, they are applying too much force. Then they reduce the commands through the EMG electrodes under the socket to open and close these fingers and then control the force. It's not a long video, let me just show you. It's real time, it's with real people, and here is the data from the sensors. If I can just show the next slide. As you can see here, without sensory feedback, the force they apply on that box can be up to 70 Newton, around 7 kilograms. By either using electrotactile feedback or mechanotactile feedback, this force significantly reduces to around 15 Newton, from 70 or from 40 to 15. And these are all live data, just without any training, etc. So this is what we have been doing, so I don't want to bore you with too much technical details. And as a group, as a team, we made some significant progress, and without saying too much, and also, of course, we did this one in collaboration with many people. We thanked them, and this slide will be shown later if you want to email me or Gordon or anybody about further information. So these are the people we have been collaborating and working together, and we are grateful to all of them. And we are here today to identify new partners, new collaborators, to do research together, to do clinical trials, to take this technology to the next level for commercialization, or use our expertise in smart sensors and actuators and their application in robotics and smart systems. We can apply to a range of problems, a range of research problems. We have the expertise, although this applies to the prosthetic hands, this expertise can be applied to any projects where actuators and sensors and additive manufacturing, additive 3D printing can be applied. So without saying too much, I will just stop sharing, and I will just return to the main screen where the hand is. Before we go further, I just want to show you this electrode I was talking about. So you see, I got the electrode I was showing you. It wasn't too big. And another point I was talking about, that armband with the 3 motors, although the figure was there, we just built this one to put on the arm. And these are the ones I just want to show you. And lastly, the finger I'm talking about, as you see here, you can see the compression in the tip of the finger, where we have pressure sensors like our flash. As soon as the finger touches an object, we can control the movement of the finger and control the force between the finger and the object as well. And I thank you so far for listening, and please feel free to put your questions, which we will answer. And before going further, now it's through Dr. Zhou to demonstrate the operation of the hands. To you, Hao?
Yeah. So good afternoon, everyone. So the whole system, including 3 parts. So the hand for sure, and we also wearing the EMG sensors to taking the biosignal from the forearm, and we send this biosignal into at the moment we use the PC to processing all these data, so it can recognize different hand gestures. In the future, we will develop some portable device to handle this pattern recognition, such as like the iPhone or some iPad. So for the pattern recognition system, it includes 2 steps, mainly include 2 steps. The first step is the training step. So in the training, we want to make sure we have good quality data. So we we taking each hand gesture. We want to do open, close, pointing, pinch. Then we record this data. So then we go to the second step to have some new incoming data. Then we classify this data to control the hand. So now I'm gonna do some little demonstration. So I'll do pointing, closing, pointing again, opening, pinch, opening.
Yeah, you're talking faster than the hand, huh?
Then we can do some wrist movement as well. So as you can see, the advantage of the pattern recognition is the traditional control of the prosthetic hand is only on and off. So now with the pattern recognition control, so we can we don't need to switch manually switch the patterns, and also for the traditional pattern recognition, traditional myoelectric control, every time you need to go back to the neutral position. But for this pattern recognition system, we don't have to. So every
and somebody's asking about the electrodes. How
yes.
The electrodes are on Zhou's arm.
Yeah. So this is like the armband consisting of 8 electrodes.
Yeah, it's on the Zhou's arm and it's wireless. Carry on, Zhou. Sorry.
Yeah. So yeah, that's pretty much about it. So any questions?
And as I said at the beginning, the main problem with the current hands is not the mechanical design, is mainly about the bilateral control. Can you non-invasively convert users' intention into the commands, and similarly close the loop around the user and send some feedback to the user who knows what force, what contact is happening between the hand and the environment. And I think there's a question here, what are the power requirements to power this? How? I think you did estimation for the power. Please feel free to.
So at the moment, the battery we use is 7.4 volts, and we use for this hand we use 4 motors, and usually the batteries we need about 2.2 amp hour.
Amp hour, okay.
Yeah.
And we are using 3 electric motors. Of course, if you use more electric motors, as I said at the beginning, we are using the under actuation concept, using one motor to move the tendon rather than controlling the joints of the motor. If you do so, you have to use more motors, and it means more energy.
Yeah.
Thank you, Al. And thank you for that question. That was a great question.
Gursel?
Yeah.
So how it might not have been obvious before that the hand was actually tracking your movements because we couldn't see your hand.
Oh.
Oh, you mean like the gesture and this one? Okay, yeah. we can repeat that one.
Yeah, just to show how's hand and how the hand is tracking.
Yeah, I will hold the camera. How? I think let's repeat the gestures.
Yeah.
Go to beginning. If you can reset.
Okay.
If you then I will hold the camera. That's a good point.
Maybe I'll just stand up.
Yeah. Feel free.
Can you see my hand now?
Yep. Now we can see you. Yeah. That's it. Yeah.
Closing.
Yeah, very good. That's the story.
Yeah. And
yeah, that's the screen.
And Gursel, is there, well, how's doing that? Is there anything peculiar about the actual hand design in itself? I can see that there's joints that are strategically placed get those movements. But are there any other features of the actual structure of the hand that are important?
Yes, indeed. Very good question, Gordon. Thank you very much. Especially the movement of the thumb, which is the most important thing. All the fingers are important, of course. We made sure that the thumb normally has 3 degrees of freedom, even more perhaps. What we did, we came with an idea to have 2 degrees of freedom, thumb doing this and moving forward as well to the side, and this one using 1 electric motor. Plus, of course, that was a very smart idea, using 1 electric motor to get 2 degrees of freedom. Plus here, and maybe I will show you here, I think the hand is here. We use the concept of flexural joints to make sure that it bends forwards and it doesn't bend backwards. So when we push these fingers backward, it doesn't go backwards like our finger. So in our finger, you see, it comes forward, but you need to break it. So that's why in this new design, latest design, the joint is in the middle. I don't know how we can focus, perhaps if I have a sample of this one. We got another hand, sorry, we have a spare hand. If I can just, without breaking it, maybe I'll show you this screen. This one, yeah, as you can see here, see the joint is 3D printed. This is the front part that makes sure that we got enough space to bend. Okay, like our finger, and this range of motion is the same as the range of motion for our finger. But more importantly, at the back, we got a constraint, it doesn't go backwards. You see, it just blocks like our bones to make sure that it has enough strength to support the weight like a straight open hand. Oh, yes, thank you, Hal. I'll remind me something, of course. One thing I said at the beginning, we put the sensors in the mechanical structure. So what we did, while on the same screen, these joints, see, it doesn't go back. And we have also here a chamber in the middle, and it has air inside. When this bends, in proportion to the bend, the sensor generates an electrical signal, and we can estimate the bending angle of the joints. And we use these sensors embedded in here to control the position of the finger. And similarly, another sensor is here at the tip, as I mentioned before, to control the tip force and the gripping force. Look at the nail, you can make the nail part as well. So yeah, that's another thing. One thing we did was that to embed sensors as part of the mechanical structure.
Yeah, and these sensors are very stable compared with the commercial sensors. They require very little calibration, which is very important for this application.
You see, this is another application. If I can just put in front of this camera, this screen, I think that's the screen you are seeing. We built a gripper, a soft gripper, to handle some objects with different hardness and softness without damaging them. So we have these soft contact pads, and we have the pressure sensors inside. By continuously reading the pressure, we can control opening and closing of the gripper. So we had a 3-finger gripper. I have one example here, a bit slightly different version, if I can. It's frozen. Is everything okay? Can you see it? Or now it's coming back, I think. Yeah. Anyway, yeah. So we got these 3 fingers. Maybe it's too much. We are asking it. So again, it's coming to the same point I made earlier, to come with designs where the sensing elements are part of how this not. Can you see anything now? No.
Yeah, you can see that.
There's a bit of problem here, but not a big issue now. So the idea was, again, to have sensorized objects and especially contact structures where the sensor is part of the mechanical structure to control it and then drive the system. I think this is one of our strengths as well.
Excellent.
And Manish asked a question. Thank you for attending this, Manish. Any plans, I'm reading a question, any plans to introduce damping to reduce vibration on full extension. Yes, there is a plan, and of course we are planning to have a simple solution to damp it out. Perhaps as you see, there is no cover on the fingers. We just showed the bare structure of the fingers. That's another thing. That vibration is a bit of non-controlled, but when it's covered in a glove in some of the stuff we had, and that was also controllable. But when we use these embedded sensors to control the position and the force, that vibration was gone. So I would say yes, plans, and it's already being considered to reduce, to eliminate that vibration. This is a fully experimental system with no consideration to show, but it's being considered already. Thank you, Manish. Any other questions, friends? And while waiting for the questions, I would like to make a point. We got a research project on using fingers embedded with the pressure sensors and use these ones to control the touch sensing, and implementing this one on a commercial hand, which is going to be lent to us. It was posted last week. It hasn't arrived. I was hoping to show you today. A prosthetic hand company in New Zealand called Tasca Prosthetics, and they kindly agreed to lend us a hand, and we agreed to have a PhD project on fingers embedded with pressure sensors, and using those fingers and a commercial hand, and our expertise in sensory feedback. Those electrodes I showed you, the small electric motors applying mechanical force. So if any of you are interested in doing PhD in sensory feedback, and please contact us, and especially we are looking for some students who are academically strong and highly motivated to apply for a scholarship offered to domestic students by the university, then we can start this project early next year in February or early March. So that's a very exciting opportunity to use the technology we developed and apply to a commercial hand, a company which is already delivering hands to the users and in collaboration with that industry. So we have a very exciting PhD project. If you are interested in, please send me a note, send me an email. I think Manish, sorry, there's another question. While I'm waiting, many questions came, which is great. That's very exciting. If I can go back where I read Manish's question. And after that one, we got Jeremy. Thank you, Jeremy, for attending. How many and what type of materials are printed in the monolithic print? I mean, here in the hand we are showing you, it has two materials, two separate materials. One is ABS, it's a hard plastic. Another one is a slightly softer material called Filaflex.
Yeah.
Filaflex. So depending on the printer we have has two extruders. You can print separately or combine together, which we don't want it. But to come to your specific question, I would say two. And the next question is from Will G. Thank you very much for attending. How about the supporting strength of these hands? Can the fingers or the structure hold a push-up like power when falling down? That's a very good question. I don't know the push-up. Of course, the force strength, force carrying capabilities of these hands are not as high and not as high as the hands made of hard materials. I think we tested this one. This can go up to 6 Newton. 6 Newton, which is maybe not much for low duty applications. I can say so, but I don't think we can do push-ups.
The palm material is made of rigid material. So it's taking more load. Yeah. That's why we specifically design the palm with a rigid material, so it can take in more load.
As you can see how he's moving his wrist, and robot's wrist is moving as well. Still, he's doing it. Yes, thank you, Hao. That's a good point. This blue material, as Hao mentioned, is made of hard plastic. But again, if you come directly onto the palm, it's fine. But for the fingers, I'm afraid there's a limit there. There's always a limit, something there. I hope I answer your question. And Cameron, I think if I can, I'm just testing my vision as well at the same time. What is the main cause of the delay between recording signal and the prosthetic responding? That's a very good question. Of course, it's wireless. There is a bit of delay there. There is a bit of computation, processing time. These are natural. But I should also tell you that we use off-shelf, low-cost components to demonstrate these hands. So our final hand will be based on some more expensive one, more reliable components with smaller delay. But still, we believe this delay is not too much to undermine the performance of that.
And also because of we using a machine learning algorithm. So there's a window, time window for this machine learning algorithm to work. Like we need taking usually 100 millisecond to 200 millisecond data. So you have to wait for this data coming in, then you processing these biosignals to control the hand. So yeah, so that's also a part of the delay, the reason of delay.
Yeah, thank you very much, Hao. That's a good addition. There's another question, and thank you for that question. Says this person says, I saw how demonstrated his hand movement, and there was some delay in the prosthetic hand, as similar to previous question, to respond. And says, would it be annoyed for the user to have the time delay? There is a limit, of course, it's annoying. You want it to be natural, like any hand, but as I said before, that's not a big obstacle. And in other demonstrations, this delay was less. And because it's wireless, that's another reason there's a delay. Certainly, we should approach to the natural movement. Otherwise, of course, it's annoying. And we are saying that we will come one step closer, at least, to the natural counterparts. Another thing is that, for example, if an obstacle is dropping and it should be caught in time, I mean, that's another thing. Of course, when there's something is coming, it's the whole arm in a way rather than the hand itself. And also, friends, we need to be realistic that we are talking about an artificial implant and device with some limitations. And when we did this survey, the users told us they don't want anything overly sophisticated, something reliable, something they can do their basic daily activities. So certainly there is room for improvement to do this kind of like catching an obstacle, catching something, dropping. These are some dream aims, but so far the priority is more about some basic daily activities. Thank you. How Emre put something. I think this is in response to Mani's question about vibration, and Emre is one of our collaborators and lecturer in our school, and he's also a co-author on this paper. We use those fingers with embedded sensors to control its position, and the solution is in that paper, just accepted for publication. Thank you, Emre, for offering that additional answer. Another question, maybe I'll come closer to the screen, colleagues. I'm relying on my eyes, but I don't want to miss some important questions by reading slowly. Maybe I'll just put my glasses this time. Harrison asked the question. Thank you, Harrison. Can the sensors in the fingertips only sense the pressure on the fingertip, or are they able to discern between normal or shear forces? Current ones, the one we showed you, can sense the pressure, but at the same time, we are working on some capacitive sensors. We can discriminate between the normal and shear forces. So that's also possible. But the one I show you is the first one. Yes, there is a plan to integrate directional force sensors. This is the part of the PhD project I mentioned, to have sensors which can identify a normal force as well as detect the slip, which is the shear force. That's a very good one. Thank you, Vladimir, for attending. And what is the programming language used to control this prosthetic hand? We used Python. Python was used, any program, C++, depending on what is at your disposal, but currently Python was used. Next question from Farhan. Thank you, Farhan, for attending. Can the sensory feedback sensors distinguish between the different intensities of force applied, and can users distinguish it? Yes, we have 3 intensities currently, but this can be maybe increased. It can distinguish between those 3, as the sensory feedback video I showed and the graphs, we show the decrease in the force. They can clearly see the difference between the force level they applied on the object, and then adjust the command to the electric motors opening and closing the hand. So the answer is yes. We got another question from Dulanyana Manoj. He's or she's asking, what is the classification system? I think we use support vector machine. What did we use how for the pattern recognition?
We use a couple of them. One is a random forest,
yeah,
and also use SVM, the support vector.
Yeah. And what's our accuracy?
The offline accuracy is very high. It's over 95%.
Yeah, 95%. And also, if I can just expand on this one, the armband, how is using its accuracy was around 88%, and the one we developed, the one I was just talking about, maybe I'll come closer. Anyway, I think the focus is somewhere else, and it's also 95%. So that answers that question. Next one is from Alistair Simpson. Thank you, Alistair, for attending. The question is the grip strength comparable to an actual hand? Is there currently a limitation in the range of force possible? I don't want to say it's comparable. The actual hands, of course, depends on the person, gender, age, child, man, woman. It changes, so it's typically around, if I say at least should be 25 Newton. Currently, the one we showed you also depends on actuators. The motors we use are small motors, which we made sure that they fit in the palm of the hand. So by using certainly high power electric motors, we purchase those motors, we'll put in the next hand. And then the force currently is around 6 Newton, and which is not comparable to the hand, but this is, I think that's the way we will go. Next one is from Andrew Gillette. Andrew was a previous member of our research group, one of our undergraduate students. Welcome, Andrew, great to hear from you. He's saying that the soft sensors are currently manufactured by 3D printing. Do you see it possible to manufacture the embedded pressure sensors in the fingers using any other manufacturing processes? Why not? So the reason we use 3D printing was that while we are printing the fingers, while we are printing the hand, we just wanted to print the pressure sensors or pressure sensitive chambers using one process without any new processes. As long as it's economically viable, as long as it's compatible with the rest of the finger, I don't see any problem. Some people use molding techniques, some people use other techniques, maybe surface printing, screen printing on the surface can be another way to print perhaps some sensors on the fingers. But when we talk to the prosthetic hand company I mentioned, Tasca Prosthetics, They want sensors to be part of the finger, like our finger, like the flesh. And in fact, what we did is like that. And the next question in Andrew's question is, what materials would you choose to use? Again, depends. If it's depending on transduction method, it's piezoresistive, or that has its own problems. If it's capacitive, then it's the parallel plates topology. There are lots of materials, smart materials, conductive materials, graphene ink, carbon nanotube. Lots of things can be used depending on application, depending on what specific requirements are put forward. A range of materials can be selected. As I said, ACES has a large group of people. We are 200 people in ACES, and electromaterials is one of the main strengths in ACES. If anybody comes with any application, specific application, I'm sure will come with a good set of materials to suggest materials for sensors. And the next question is it within the scope of your project to investigate alternatives to 3D printing? Not initially. This is not within our scope. It depends on funding, of course, there's a limit. But if there is room to look at other manufacturing techniques, yes, we are open to look at other techniques I just mentioned. Thank you, Andrew. The next one is from Zarko. Does external acoustic noise or electric field interfere with pressure, with pressure or capacitive sensors? So if return, as far as I know, for pressure sensors, I don't think we have that interference. And for capacitive sensors, it's the same. We didn't use it here. Currently, one of our PhD students and the research fellow is separately quantifying soft capacitive sensors, which are highly reliable with minimum hysteresis, no creep. And we tested for at least 10,000 cycles, still stable, and we didn't see any noise whatsoever. And if you are interested in, we can further talk about this one. Next one is from Tian Huang. Thank you for your great presentation. Thank you to you for attending. Can you share any advantages of your pressure sensor design compared to other 3D printed soft sensor? We got a publication on that one, Tian. It's stable, and it's minimum hysteresis. Hysteresis is almost linear. There is no hysteresis, there is no creep, and long life. And that's why we selected them. So we selected pressure sensors after thoroughly characterizing them to make sure that they are suitable for the application we are considering. So I can give you more if you are interested in that one. Are there any limitations of the sensor? Limitations, current reading is not that high. I don't think how much pressure we can, it's not in top of my head. I think there's a limit, maximum pressure you can read. But that's not our aim, because we are talking about contact detection in prosthetic hands. We didn't aim to have highly sensitive, highly linear pressure sensors with high reading. So I would say this is one of the limitations. Another thing is, of course, we design the soft chamber. We buy some solid state pressure sensors and we just assemble them together. This can be another disadvantage depending on applications. And there is another one from Tilling, but no questions. Thank you, Tilling. Andrew asked another one. Thank you very much, Andrew. Great to read your name. I didn't see you, but you saw it. Thank you very much. And thank you, Gordon, for this one, for giving us this opportunity. As I said at the beginning, this is priceless to come out and share what we have done and what we can do as a team. As I said there, please, this is just a short small sample of what we have done. And here is our team, our facilities. We got world-class facilities. under ACES, under ANFF, whose headquarters are at the University of Wollongong. And we believe if we interact with the end users, with industry, and understand what they want, I'm sure we can come with a solution to solve their problem. And we have the capacity, we have the team expertise, and the mindset to work with a diverse group of people to handle some challenging research questions. And thank you, Chilling. Maybe lastly, the question that I will come to you, Gordon, you will wrap up, I guess. Tilling is asking very good research topic. I wonder the control of the finger motion wouldn't be an easy task. Could you talk a little bit about control? As Emre mentioned in response to Mani's question, it wasn't challenging. Our advantage was that sensor was part of the finger. And I mean, if Emre is there, he can tell more about that one. What we did was that we didn't go for an advanced controller. We deliberately didn't want to go for an advanced controller. We used a PID controller. One thing we did was that even the stiffness of the object was changing. We didn't have to retune our controller. The beauty was that our controller was insensitive to the stiffness of the object, stiffness of the environment. That was a great advantage of using soft sensors. So it could easily adapt to various context situations with no problem. So implementation was simple. We didn't want to go for advanced controllers. We relied on the design. We tried to put some intelligence into finger itself to put minimum pressure on the control, I would say, tilling. So it wasn't a tough control problem to crack. Next one, Arman Gambir. I was wondering how financially viable this prosthetic will be as a product to consumers. As I said at the beginning, one of our aim was to come with an affordable solution, which we came. We did a simple cost analysis. Again, we used some very simple off-shelf components, not expensive. Of course, the expertise is priceless. The expertise in ACES, in our colleagues, with us. It's at least, I think how you mentioned this one, the price is 1/5, or how much you did a bit of simple analysis?
If only think about the material cost only a few $100, very cheap compared with commercial hands.
I think it will be much more affordable. Of course, there's a big monopoly in this field. And one thing we have to be realistic, because these are customized solutions, and also getting approval from the regulatory bodies is very expensive. That's another thing we have to all consider, the cost of medical devices. But we believe using the current progress in additive manufacturing, smart materials, and soft robotics, the cost can be cut and make these systems more affordable. And we can deliver solutions to these important problems. So that is something we have to work together, but financially I can say is more viable than what's on the market. That's a very important question. Thank you, Arman. And are there any other questions? If not, maybe I'll pass to you, Gordon. Would you like to say a few more words, or if I can put your screen on that as Gordon, as our director?
Just very quickly, big thanks to Hao and Gursel, and of course all of the team involved in our soft robotics work and the prosthetics work. Excellent, exciting advances there. And as Gursel said right at the start, if anyone online would like to contact either Gursel or myself around developing new partnerships that can help us accelerate progress, please do so. This is one of those areas that we've worked very hard to get to this stage with Gursel and his team, and keen to make sure that we deliver real practical applications out into the communities that we're working for. So thank you for attending, and on behalf of all of you who are attending, a huge thanks again to Gursel, Hao, and all of the team. Thank you.